So let me then move to the more interesting thing about, well, the first basic application of Taylor series in multivariable setting. Okay, so we looked at motion of a particle in a plane. So that's physics wording of, well, or description of the situation. Right, so you think about a particle flying or moving in a plane, and then you describe the motion by giving position. So position is going to be a position depending on time, but position now is a pair of coordinates. So there is a coordinate system out there, x and y, and position is described by providing x of t and y of t simultaneously. So that's what position is. And now, as we look at what the position is, what we see is two functions, and those are real functions from calc 1. One number depending on the other. So this is the setting when Taylor series applies. X of t can be written as Taylor series. Y of t can be written as Taylor series. So let's write them. X of t is, well, of course, to begin writing Taylor series, we have to fix some moment t0. So t0 is not that point, right? This is the position of a particle at the time t0. And then x of t is x of t0 plus x prime of t0 times t minus t0. That's the first degree Taylor term, plus x double prime of t0 over 2 times t minus t0 squared. And of course there are more terms to make the equality happen. Y of t can also be written as y of t0 plus y prime of t0 plus the second derivative plus third, fourth, and so on. Now, what is it that they're gaining from these two Taylor series? Well, of course, each of them approximates respective coordinate. But now we would like to extract some geometric meaning of those things. Not coordinate, not numerical meaning, but geometric. And what we can do is we can pair those x and y. And that pair describes the position. So this is x of t, y of t, the exact position of a particle at time t. And then we can pair things together, because these two numbers together give you position of the point at the time t0. This is what it is. What happens if you pair these two together? Those two together give you velocity, vector, right? Not a scalar anymore, but a vector that you can imagine as a vector at that point, because we evaluate that at t0. So this is position point, this is vector at that moment. What if we pair these together? Well, the numerators make together acceleration. So we have acceleration at the time t0, velocity vector at the time t0, and position, let's call it p at the time t0. And what we have is position at any time t as a point on the plane is equal to position at time t0 plus the vector of velocity multiplied by t minus t0 plus the vector of acceleration divided by 2, well, 2 factorial technically, multiplied by t minus t0 squared, and you can continue. Right, the next will be a vector made by third derivatives, that's the jerk, divided by 3 factorial, multiplied by t minus t0 cubed, and so on. So the outcome is a Taylor series, now in multivariable setting. Now you operate with vectors in the appropriate space, and then you describe the motion to any precision you want. And we can follow that from physics point of view. Right? The complicated motion is basically no motion. You stay there at one point, but that's not a good description. So you say further that, well, you stayed at that point, but then you began moving with the constant velocity vector. That's a better description of a motion. But you know there is acceleration, so you can think of constant acceleration motion. But then acceleration may change, and you may think of a jerk, constant jerk motion, and so on. So there's gradual improvement of our description of a motion.